Hello, we're going to continue with Kirchhoff's laws. Previously, we looked at what are Kirchhoff's laws, right? You know the observation. Now you put a name to it, law. Oh, that law called Kirchhoff. Okay. But we're going to continue looking at Kirchhoff's law, and your circuits will slowly get more and more complicated. But don't worry, you'll be equipped with the skills to hopefully solve them. Anyway, today we are going to look at ta-da, how to use Kirchhoff or Kirchhoff. Oh, did I say Kirchhoff again? Never mind. Kirchhoff's law to derive equations. So when you see this word derive, it means we're going to look at the origin story of some equations already. So what are the equations for combined resistance? There's two of them. If your circuit is in series, okay, refresher of chapter 19, then your total resistance will be all the resistors in series R1 plus R2 plus R3 plus however many you want. No? If you have resistors in parallel with your battery, then you have to do this funny thing called 1 over R total equals to 1 over R1 plus 1 over R2 plus 1 over R3 and so on and so forth. Of course, if you want to find R total, then you have to rearrange on. R total equals to invert everything. So, can't see. 1 over R1 plus 1 over R2. Wait a bit. Negative 1. The negative 1 means 1 over. Okay lah, just a reminder. Okay. So we're going to learn where these equations come from. Since you use it, you must know where it comes from. Then, of course, we're going to look at some refreshers of chapter 19, how to apply these two equations in all different kinds of situations, different kinds of circuit. Okay, let's go and see how to derive the equation for resistor in series. That's the first one. To do that, I'm going to use OneNote because it's easier to write. Anyway, here we have a classic circuit. You have a battery. I put a dotted line. 3 resistors connected in series. So I'm going to call this resistor 1, resistor 2, and resistor 3. What's inside this battery? Well, you have the battery EMF. We use this thing. But also to symbolize that your battery has internal resistors, let's include that as well. So little resistance. So let's call this small r. This one we call EMF. Okay? So in this case, only one battery. So the current will flow out of the battery. We call this current I. Sure, let's call it I. Then you have a current flowing through the first resistor, so we call this I1, call this I2. You say, Miss, shouldn't it all be the same? Okay, wait, yes, hang in there. Okay, then the battery current will flow back. Same current flowing through everything, because, charge cannot go anywhere. So the first thing we need to think of is, what I just said. You have current I equals to, this I is the same as this I1, which is the same as the I2, which is the same as I3. Because in series, the same current will flow through. And what law is this? Conservation of what? We say conservation of charge, because your charge has to go somewhere. They can't just appear or disappear. So this is actually Kirchhoff's first law, K1, that deals with current, okay? K1 is Kirchhoff's first law. Let's do another thing. Let's use Kirchhoff's second law. Now, the second law says you have your potential drop across your EMF, this one here. Let's call this E lah. I already write that E, no need to write again. Also, I need to make this a bit smaller. So we have E. Then this total energy supplied to the circuit should be equal to all the potential drops. So you have this potential drop called V1, this potential drop called V2, this potential drop called V3, and of course you have this tiny one from resistor, which kind of what we call the lost volts. Okay, you have EMF, but you lose some lost volts, so what actually goes to your resistor is a little lesser. So if you add them all together, EMF equal to, you have V1, V2, V3, and also VR if you want to take that into consideration. And this, of course, you can rewrite into what we say IR, or all those things. Let me just rewrite this. So we have V1, which is I1 times R1. I1 here, I1, R1, I2, R2, because V equals IR. Okay, so I2, R2, V. Why did I write V? Just use this. Erase. Now it's working. Okay. So next one is I3, R3, and then of course, what's the current flowing through this internal resistance? Just IR lah. Okay lah, IR. So we have IR. Okay. And this one E is what? E can just V equals to IR, E equals to IR. But what R? You can just have the big I times R total. Total resistance of all these resistors in the circuit. So R total. Then what do you do with this thing? Oh, also this one is which law? This PD, sum of EMF equals the sum of PD, Kirchhoff's second law. So it's K2. Don't confuse what is the K1, K2. Then what do we do next? The third step is you have two equations. So if I do, divide equation 2 by equation 1. If I do, then what do you get? 2 divided by 1. You take IRT divided by I. So that's left RT equals to I1R divided by I, which is the same thing. IR divide everything by I lah, then all gone already lor. So all you left is RT equals to R1 plus R2 plus R3 plus mini R. And where have we seen this before? This is the equation for resistors in series. If you have anything in series, you just add their resistance together. Done. Okay, so that's how you can deal with things like that. Now, what if you have resistors in parallel? How do you derive the equation to calculate that? Okay, this is the other one. So same thing. We have EMF, battery. I'm lazy to include the resistance, so I'm not gonna. Internal resistance also for now. Let's just look through this. Okay. So we have E, and the current will come out of the battery. Let's call this I. Then as you come to what is this called? A junction. Then you will have a current split. Some current will turn right, some current will go down. Let's call the one that turn right I1. Then come here, split again, got another junction I2. Split another junction I3. Also, we can give this resistor some names. Why not? R1, R2, R3. 10,000 ohm, 5 ohm, whatever lah, you choose the ohm. Okay, so now we got the main thing set up. So we're going to do something very similar to what we did just now. First step, I want you to think of the current. How does I1 and I2 and I3 relate? All this. How does all this orange color I relate? Are they all the same? No. You think of, actually they split. I, the original one, is actually all of them added together. So you can write I1 plus I2 plus I3. Because I1 split into I1 plus I2 plus I3. This is what law? We have seen this before. What law is this called? This is Kirchhoff's first law. The current one, conservation of charge. Okay, your charge has to go somewhere. So when they split out what you have, you split. Okay, then the second step, you might have guessed, we're going to do something similar also. You want to think about the sum of PD. Ooh, this one is kind of interesting. So yes, you have EMF that is providing energy to the circuit. But what is the potential difference across each of these resistors? Think of it this way. All these lines are in parallel, right? So if this one here have a PD of E, means this one here have a PD of V1, this one PD of V2, this one PD of V3. And they're all the same. Why? Let's say your E is 12 volts. That means you come up here, these are all 12. My saliva dry already. 12. Then once you drop, then only you go down to 0. So here is 12, 0. That's a potential drop. You see the drop from 12 drop to 0 because you must return at 0. So it gives all the energy. So this is all 0. That's why I call potential drop. Top of waterfall, drop down to 0. So the thing is, you can say now it's the other way. E equals to V1 equals to V2 equals to V3. Where is this from? Kirchhoff's second law. So we put a note here, Kirchhoff's second law. This is true for parallel lines. Okay, then you might have guessed the third step. What are we going to do? Third step, let's divide. You want me to write more step? Okay lah. I want to write lah. I just say let's divide. Say what shall we divide? Let's divide 2 by number 1 to get resistance, because you know V equals to IR. If I want resistance, I have to do V divided by I. Okay, so 2 divided by 1, 2 is all the E stuff. So how to divide leh? You just say lor, every time got E got V is the same thing. Actually, hang on a second. I noticed an error. Not 2 divided by 1. Wrong way. This is 1 divided by 2. Why 1 divided by 2? Because you want resistance, so V divided by I later. Okay, so you'll see why in the next second. So I rewrite I equals to I1 plus I2 plus I3. Okay, and this I, the first one orange here, is related to the EMF of the battery. So the first I is EMF of the battery divided by the total resistance. That's how you get the big I there. Okay, total resistance, all the resistors inside there. Okay, then the second I, let me rearrange a little bit. I equals to V over R. So this one will be V1 R1. Then I2 will be V2 R2. I3 will be V3 R3. You say, Miss, this does not look like all the thing. But never mind. We want to divide everything by 2 ma. So when you see this or this or this or this, you can divide out. So I divide everything. The E is gone, the V is gone, everything's gone. So all that's left is 1 over RT plus 1 over R1 plus 1 over R2 plus 1 over R3. Because the reason is, I mentioned here, divide by E or V or V or V. Anytime you divide the whole circuit by number 2 already, so all this is gone. Divide both sides by E or V. Then you have this final equation. This is how you can combine the resistance of parallel resistors here. So R1, R2, R3. Combine, you find R total. You will see some books write it in another form. It's the same thing. But if you see them do RT equals to bracket 1 over R1 plus 1 over R2 plus 1 over R3, or how many parallel lines you have, -1, it's the same thing, because here see 1 over ma. Okay, so this is just another way of writing it. Might be easier to type in your calculator as well. Alright, so these are the 2 ways you must know how to derive these 2 equations. They will ask you in paper 2. You'll see some practice questions that have that one. So now we're going to look at some example questions, how to use these 2 equations to solve circuit problems and simplify our life a bit.